If you've worked with large language models, there is a chance that you have at least heard of the term RAG, or Retrieval Augmented Generation. The idea of RAGs are pretty simple. Suppose you want to ask a question to a LLM. Instead of just relying on the LLM's pre-trained knowledge, you can first retrieve relevant information from an external knowledge base and then pass this retrieval information into the LLM along with the original question and allow the LLM to generate a more informed and up-to-date response. For the LLM, this is like an open book exam where we are asking it a question but also giving it a book which has the answer written down somewhere, and the LLM must use its comprehension and reasoning skills to find where the answer is located in the provided context. RAGs are a cheap, practical way to use LLMs to generate content about recent topics or even niche topics without needing to fine-tune them on your own and burn away half of your life's savings. In this video, we're going to start with the most basic bare bones RAG pipeline and then identify how each of these components work and how modern frameworks have made it ultra powerful and ultra reliable with some pretty crazy innovations. This is Neural Breakdown. Let's go. RAG. Let's say our goal is to make a simple API where we receive questions from users in form of a text query, and our bare bones RAG pipeline will answer these questions based on a database of Wikipedia articles. I'll make a simple workflow diagram on the foundation blocks of RAG using this video sponsor Eraser.io. Let's take a moment and think about what building blocks do we need to build this simple pipeline. Well, first we need a database that contains all the documents. Second, we need a query processing method to convert the user query into a searchable query. Third, we need some sort of a retrieval or search strategy that could perform similarity search over our database. And fourth, we have the post-retrieval stage where we must generate the answer from the retrieved documents. So far we have only discussed the inference part of our RAG pipeline, meaning what happens when the user poses a question to our API. But even before deploying this server to the public, we have to have an offline pre-processing stage where we had created that database in the first place. And it also contains 4 stages. First, depending on the application we are building, we must identify our data source, like Wikipedia article. Second, we need to break down the dataset into smaller documents or chunks that we would insert into the database. Thirdly, we must convert these chunks into a searchable format, like converting them into numerical vectors, for example. And fourth, we need to insert them into our database. Now, note that you don't need to have a database to build a RAG. Many RAG pipelines use Google search or similar search engines to just call existing databases through a search API. But for the purposes of this video, we will just talk about the general use case where the database is also our own creation. Great, so we have identified several key modules required to build a RAG. But believe it or not, each of these components have a lot of additional research to make this simple looking RAG turn into a CHAD RAG. Eraser also provides this nice markdown editor, and I'll share this markdown and the diagrams I made in the description below if you people want to have a look or use it later. Meanwhile, let's look at each of these modules and see how we can improve it further, starting with chunking. Chunking is the process of breaking down large documents into smaller, more manageable pieces. It might sound simple, but trust me, the way you chunk your data can make or break your RAG pipeline. Whatever chunks you create during pre-processing will eventually get retrieved during inference. So if you make the size of the chunks too small, like each sentence, then it might be difficult to retrieve them through any kind of search methods because the chunks capture very little information to search on. And if your chunk size is too big, like inserting entire Wikipedia articles, the retrieved passage might end up confusing the LLMs because you're sending large bodies of text at once. A common algorithm is to set a chunk size hyperparameter. and then loop over each sentence in your dataset and maintain a list of chunks that are all smaller than your targeted chunk size. You can play with the hyperparameter to see what results you get at the end of the pipeline to see which chunk size is the best performant for your task. The propositions method extracts simple factoids or propositions from the text corpus and treat each of these facts as documents. Now, be aware that all types of LLM-based chunking are quite expensive because the larger your dataset, the more LLM calls you'll have to make. Also, quite often we may also deal with datasets that inherently have a known structure or format. For example, if you want to insert code into your database, you can simply split each script by the function names or class definitions. For HTML pages like Wikipedia articles, you can split by the heading tags, for example, split by the H2 tags to isolate each subchapter. But there are still some glaring issues with the types of chunking we have discussed so far. Suppose your dataset consists of tens of thousands of paragraphs extracted from all Sherlock Holmes books. Now the user has queried something general like, what was the first crime in The Study in Scarlet? What do you think is going to happen? Well, the problem is that since each document is an isolated piece of information, we don't know which chunks are from The Study in Scarlet. Therefore, later on during retrieval, we will end up fetching a bunch of passages without knowing if it's even relevant to the book. To resolve this, we can use something known as contextual chunking. A recent blog post from Anthropic describes it as prepending chunk-specific explanatory context to each chunk before embedding. Basically, while we are indexing, we would also include additional information relevant to the chunk, like the name of the book, the name of the chapter, maybe a summary of the plot even. Because adding this context will allow the retriever to find references to Study in Scarlet and crimes when searching, hopefully getting them some right documents that they can use to answer the question. Also, there are some other ways to solve the problem of finding the right queries like metadata filtering, but we will talk about this later when we talk about databases. For now, let's talk about the problem of data conversion. The goal of data conversion is to convert your text chunks into an indexable format that could be easily searched for similarity matching. Whatever strategy we use to convert these documents during this offline pre-processing stage, we also need to use something similar to convert the query during inferencing as well. Two of the most common approaches that have emerged in this space are embedding-based methods and keyword frequency-based methods like TF-IDF and the BM25. We'll start with embedding-based methods. Here, we use pre-trained transformer models to transform the text into high-dimensional vector representations, capturing the semantic meaning about the text. Embeddings are great for capturing the semantic relationships, handling synonyms, and understanding context-dependent meanings of the input documents. However, embedding can be computationally intensive and can sometimes overlook exact matches that simpler methods would easily catch. For example, suppose you have a database of manuals containing information about specific refrigerators, and when you ask a query mentioning a very specific niche model or serial number, the embeddings will fetch documents that kind of resemble your query but may fail to exactly match it, thereby making all of the retrieved documents kinda useless. And that brings us to the alternative of embeddings retrieval: keyword-based retrieval. Two popular keyword-based methods are the TF-IDF and the BM25. These algorithms focus on statistical relationships between the terms in the documents and the queries. TF-IDF weighs the importance of words based on its frequency in a document relative to its frequency in the entire corpus. See, every document in our dataset will be represented by an array of TF-IDF score for each word in the vocabulary. The indices of the high values in this document vector tells us which words are likely to be the most characteristic of that document's content, because these words appear more frequently in this document and less frequently in others. But TF-IDF does have some issues. Let's say among our database of refrigerator manuals, we have two documents: a short, concise manual for the Godrej A241GX and another comprehensive 50-page guide covering multiple Godrej refrigerator models, including that A241GX. Now, if a user queries Godrej A241GX cooling issues, which document do you think TF-IDF is likely to retrieve? Well, with TF-IDF, the longer document might get a higher score simply because it mentions Godrej and A241GX multiple times due to its length. BM25, an evolution of TF-IDF, incorporates document length normalization and term saturation, meaning that it adjusts the TF-IDF scores based on if the document itself is longer or shorter than the average length of documents in the collection. Term saturation means that as a particular word appears too often in the database, its importance decreases. And because BM25 normalizes for document length, the 50-page book will no longer have any unfair advantage over the 5-page one. Also, super common terms like Godrej and refrigerator will also be downweighted because they appear a lot due to term saturation. So the long story short is TF-IDF and BM25 are great for finding documents with specific keyword occurrences when they exactly occur. And embeddings are great when finding documents with similar semantic meaning. These days, a common thing to do is to basically use both keyword and embedding based methods to retrieve documents and then combine them, giving us the best of both worlds. If you're enjoying the video so far, please do hit the like button and share it with your friends. Do check out my Patreon, where I will be uploading all the documents and assets that went into producing this video. Also, just a huge thanks to all of our channel members. You guys are truly magnificent. Let's get back to the video and talk about databases next. Honestly, a whole different video could be made just to unpack databases because it's a pretty complex topic. The most common type of database that is used in RAGs are vector databases. Vector databases store documents by indexing them with their vector representation, be it from an embedding model or TF-IDF. Vector databases specialize in fast similarity checks with query vectors, making them especially ideal for RAGs. Popular vector databases that you may want to look into are Pinecone, Milvus, ChromaDB, MongoDB, and they all have their pros and cons and pricing models. I'll leave an article in the description below for you to read further about comparing them. An alternative to vector databases that's also used are graph databases. Graph databases store information as a network of documents, with each document connected to others through relationships. These are especially useful when the query requires some global understanding of a concept. For example, if the query is what courses did Harry Potter take on his 5th year and who taught them. So if you had a graph database and all of the text that were about Harry being in a class or taking some course were connected together in a subcommunity within the graph, it might be easier to answer this question with graph databases, because not only can you fetch a single node from the graph, you can basically fetch entire clusters and connected nodes along with it, giving you more context of your original question. Many modern vector and graph databases also allow properties from relational databases, most notably metadata or attribute filtering. If you know the question is about the 5th Harry Potter book, it would be really nice to filter your entire database first to only contain documents from the 5th Harry Potter book and not run an embedding search through the entire dataset. Optimal metadata filtering in vector databases is a pretty amazing area in computer science research, and I hope to cover it in a separate video one day. I'll leave some links though for you to read about until then. Next, let's move on to inferencing, starting with query transformation, which is any pre-processing step we do to the user's actual query before doing any similarity search. Think of it like improving the user's question to get better answers. In general, we want to avoid searching directly with the user query because user inputs are usually very noisy and they can type random stuff, and we can't rely on the quality of the user's query for our pipeline to work. And so we create an additional transformation layer that interprets the user query and turns it into a search query. And the most common technique to do this transformation is query rewriting. Imagine someone asks what happened to the artist who painted Mona Lisa. Well, if we do semantic or keyword searches, the retrieved information will all be about the Mona Lisa, not about the artist. A query rewriting system would use an LLM to rewrite this query. The LLM might transform this into Leonardo da Vinci, Mona Lisa artist, and that will be a much more fruitful search. Sometimes we would also use contextual query writing, where we might use additional context like using the older conversation transcript from the user, or if we know that our application covers documents from, say, only 10 different books. We can have a classifier LLM that classifies the user query to detect which of the 10 books we are being asked about. Also, if our database is in a different language, we can also translate the query using query translation, which is also a type of query rewriting. And there are also powerful techniques like HYDE. which stands for Hypothetical Document Embeddings. HYDE uses a language model to generate hypothetical answers to the user's query and do similarity search with these hypothetical answers to retrieve the relevant documents. Another technique is multi-query expansion, where we generate multiple queries from the single user query, perform parallel searches to retrieve multiple sets of documents, and then do a deduplication step or rank fusion to remove duplicates. There are also multi-hop techniques like Boolean programs. They work by performing an initial search, analyzing the top results to find frequently co-occurring terms, and then adding these terms to the original query. This adaptive approach can help bridge the vocabulary gap between the user queries and the document content and help retrieve better documents when run in a loop. Now that we have retrieved our potentially relevant documents, we can add another post-retrieval processing step before feeding information into the large language model for generating the answer. We can do information selection and emphasis, where an LLM selects portion of the retrieved documents that could be useful for finding the answer. We might highlight key sentences, do semantic filtering where we remove unimportant paragraphs, or do context summarization by fusing multiple documents into one shorter document. The goal here is to avoid overwhelming our LLM with too much diverse information, which could lead to less focused or accurate responses. Often, we will also do multiple queries with the query expansion stuff discussed earlier, or use multiple retrieval algorithms like Embeddings plus BM25 to separately fetch multiple sets of documents through multiple different channels. And to consolidate all of these different searches, we will often use re-ranking methods like the Reciprocal rank fusion. RRF combines the rankings from all different approaches, giving higher weight to documents that consistently have ranked well across multiple search methods. In the end, the top K high-ranking documents are passed into the LLM. FLAIR, or Forward-Looking Active Retrieval Augmented Generation, is an iterative post-retrieval strategy. Starting with the user input and the initial retrieval results, an LLM iteratively guesses the next sentence. Then we check if the generated guess contains any low lock probability tokens like indicated here with the underline. If so, we call the retriever to retrieve useful documents from the dataset and make necessary corrections. And this process is repeated in a loop until the LLM thinks it has arrived at the correct answer. So there is still some more things left to discuss about RAGs, but for the purposes of this video, that's my time. I'm going to draw a line here. Thanks a lot for checking this video out. Make sure you hit the like button and subscribe for future videos. Also, do check out our Patreon page because it's magnificent. I'll see you in the next one. Goodbye.